Okay, so let's try to get started. So, welcome everybody. Thank you for joining our seminar today. And I'm very happy to be introducing Nicolai Meinshausen as our speaker today. Nicolai obtained his PhD at ETH Zurich in 2005. And then he went on to spend a couple of years at Rice and Berkeley, at Berkeley, working with Bing Yu and John Rice. And then he spent 7 years as a professor at the University of Oxford. He then moved back to ETH in 2013, and he's currently an honorary fellow at the University of Melbourne and the head of fundamental research at Citadel Securities. So Nicolai is going to be talking to us about GC Magic, reverse Markov learning for high-dimensional generative models with distributional shifts. So welcome, Nicolai, and thank you for being here with us today.
Okay, thank you. Thank you for the invitation. And you can stop me kind of anytime, right? I mean, it's just also not kind of so many, so you can interrupt me anytime you want. Hopefully. So this is about GC Magic, and I need to explain the title a bit. Just wanted to say it's joint work with Malte Meinshausen, who's the one I know the longest on the list here. My brother in Melbourne, he's in climate science. Sinwei, who you know, Tong Zhang as well for some part of it, and Elizabeth, who's in Melbourne as well. Uh, so the magic comes from portmanteau of GCMs for general circulation models, and then there's magic, and magic is an all kind of energy balance model, which has been used a lot by the IPCC in a sense for model for the assessment of greenhouse gas induced climate change. And it's one of those really simple first energy balance models, kind of, which are based on a few lines of code, just trying to measure the energy flux in and out of the atmosphere. And based on that, you can derive what is the global mean temperature going to be under a change of forcing. So, for example, if you emit more CO2. And these models have been around for a long time. And so they've been starting to be used in the 70s, for example, where you see the prediction lines here, which would start in a certain year, and the black line is what actually happened. And as a function of year, you can see some of them seem to be off, but it's just because they assumed the wrong change. So they didn't assume enough change in what the physicists call radiative forcing. So how much CO2 essentially kind of you have out there. If you plot it as a function of radiative forcing, then the predictions have been pretty much kind of spot on. But of course, this is just about global mean temperature based on a simple kind of energy balance argument. And you want to know more. So, for example, here you have all the historical data from era 5, which is historical data about temperature, precipitation, and so many more kind of variables at a fairly high resolution. So it's usually a quarter degree grid. Okay, so you want to know more than just a global mean, right? You want to know, for example, what happens to precipitation in the Mediterranean, what happens to heat extremes, for example, in the Pacific Northwest, and so on. And so what you have is you want to produce, for example, you want to be able to understand the distribution of these historical data sets like era 5 in a certain month, say May, kind of January. And then you have a bunch of forcings. So here you have 10 different kind of forcings, which are mostly related to CO2. You have solar forcing, kind of volcanic forcing, as natural forcing, and so on. And so you want to understand the full distribution as a function of these inputs. So it's a fairly low dimensional input, and then you have a high dimensional output. And for that, you just have the historical observations. But of course, if you want to understand the full physics behind it, you need information from physics. And this is where the CMIP6 data ensemble comes in. So these are different physical models which have been used to run these simulations under different forcing assumptions. And so here you see an output of CMIP6 for temperature and precipitation as well. And the goal of this project is to build essentially an emulator for these CMIP6 models. And the question is why? And one is purely computational. So a CMIP6 model at the moment to run 100 years of a single kind of simulation would take a few weeks on a supercomputer. The second reason is also that all these models have a certain bias in comparison to observational data, even though sometimes also the models are right and the observational data are wrong. That can also happen. And you can also try to extend it to run at higher kind of resolution. So these are all the data we use, which on the left, you see a bunch of different climate models, and you see, I call ERA 5 a model, but it's essentially the observational record. And I put in there a few other CMIP6 models as the test case. And so for the first bunch, I'm just going to use the purely historical data. And for the other ones, I use all data which is there, historical, and then different forcing runs for future scenarios. And so the goal is to be able to say, okay, I wanna simulate, say, a month in December from ERA 5 under these changed forcings. And it should be a generative model. So ideally, you should be able to sample from it, not just give a mean value, but actually provide samples. And the variables which are in play are, so pressure is the first one. And so you see on the left are observations, and on the right you see a model simulation at the moment coming from the model. This is the first one. Then there's temperature at 2 meters. And again, left is observations, right is a simulation from the model for the same forcing run. Then precipitation is there as well, which is a tricky one. Then there's wind speed, surface temperature, maximal temperature. So this is the average of the daily maximal temperature over a month. There's minimal temperature as well. And there's solar radiation, relative humidity. So relative is on a scale from 0 to 100. 100 would be the maximal humidity before it starts to rain, essentially. And there's absolute humidity as well, which, because the point when it starts to rain depends on, for example, how warm it is. Right. So these are the data, and so the goal is to be able to build this model which can simulate from this fairly high dimension output. So each variable in the end has a spatial resolution of about 1 million points, and so you have 10 variables, so you're operating in a 10 million dimensional space. And the two main challenges is the high dimensionality is definitely one, and the other one is to extrapolate effects to what are called unseen interactions of model and forcing scenarios. And this is related to what I said in the beginning. It's the question is there a way to remove the bias between the models and the observational record, which is something people do on an ad hoc basis, and a model like that can provide a chance to look at that bias reduction part as well. But I should also say this part is strictly not necessary. So it would also be fine without it, but we thought we have a chance to try that as well. The challenge is in the sense that you have two different distributional shifts which go on here. So you have one shift which is induced by the different forcing. So for example, if you change volcanic forcing, if you change solar forcing, if you change CO2 forcing, and then there's one other distributional shift which is caused by having a different model, as I call it. So it can be a physical model. It can also be observational data like ERA 5. And the thing is, we have data for these two shifts on their own. So because for most models, we have both historical data and we have the distribution as it's changing under a different forcing. So this would be the red change here. This is a forcing-induced shift. Then we also have data for the blue one, which is the change between the models, but it's only for historical data where we can really see kind of, for example, how much off is the MPI model compared to the observational record of error 5, or how different is the access model to error 5. And of course, what we'd like to have is to have a way to get into this question mark and because ideally we would like to be able to say kind of what is going to happen in the change forcing for error 5. And so one way to take it apart is to say, okay, we want to build a generative model. So this is the function g as a function of x, which is the forcing, m is the model index, and epsilon is kind of the noise. So the noise tells you what is the realization you're going to get from this model at these kind of forcings. And the idea is to decompose it into this blue path part, the red part, which the blue part is essentially the bias you have for historical data. The red part is the forcing part, so which doesn't depend on the model. It's just the effect you get on a changed forcing on average between the models. And then in the end, you have an interaction effect, which depends on the forcing and the model. And this is the part which is the hardest, and ideally it's kind of small. And so there are two ways to hopefully make this work, but of course there's no clear-cut way of doing it. So the first one is a question about data and modeling. And the question is that interaction term is really big? If it's really big, we might have a problem kind of doing it. And the question is about modeling. So it pays to look at these terms kind of independently, because we can estimate the blue term really well. We can also estimate the red term really well. And maybe then there's not that much left we have to fit for that interaction effect. And the second part is about the method we're going to use. And there it helps to use these pre-additive noise models. And I'm going to talk about that for a bit. You probably have heard about that from some way already, but I just want to recap kind of how, what is a lightweight way of fitting these generative models here. So I want to start with the energy score, which most of you know from this paper from Adrian Zarafri and Tilman Signiting. And the idea is, how do we assess the distribution of it? So if we have a generative model, it means we can generate observations or samples from a distribution, and how do we assess how well it's doing compared to the true observations. And the energy scoring, energy score is saying, okay, I have a fixed observation, small y, and a candidate distribution where I can sample from. And suppose I take two samples, y and y prime, from that candidate P. Then I can form a score by looking at one half the difference between the two generated samples, y and y prime, and subtracting the L2 distance between the observation and one of the samples. And the point is that is a strictly proper scoring rule. So you can maximize it if and only if your distribution P actually matches the distribution where the observation is coming from. That is called kind of P star. So you can reach equality in that if and only if P star is actually equal to P. So if you get the distribution exactly right, and otherwise your score is always going to be worse than if you had the ideal distribution. And Gresham, which some way built together with me, was saying, okay, you can use that for a really lightweight generative modeling approach. So you define a loss function for a generative model where you put in x and independent noise epsilon. As a loss function, you have a standard term, which is the L2 loss between the observation and one sample from your model. This is the first part here. And then you subtract one half the difference between two independent realizations from that model. and you're searching for a function g, which is minimizing that loss. So it's just a negative score. And the point is, if your model class is flexible enough, then you can get the minimum if and only if the distribution of g of x epsilon really matches the distribution of y conditional on x. And so you can use automatic differentiation to fit these. And we typically use pre-additive noise models for that. So where you say you concatenate the noise to the input x, and then you just have typically a deep neural network, which you can then fit by minimizing that kind of loss function. And from a theoretical side, we could show that this model actually allows to extrapolate a bit beyond the boundaries of what you've seen if you assume the data follows the pre-additive noise model. So that y is not f of x plus some noise, but that the noise is inside of the function f. And for the theory, we had to assume monotonicity as well. In practice, we don't have to do that. So one example is if you assume you have monotone function and your data comes from a pre-additive noise model with a G star which is monotone, and you assume you have some symmetric noise around it, and then the point is that regression fails in the setting in the following sense that if you have a training support for x from minus infinity to x max, so x max is the largest value of x you've seen, then as soon as you take any value of x which is a tiny bit larger than x max, then your difference between your fit and the true function can be arbitrarily large if you have a underlying monotone function, because you can't essentially control the step size you have. As soon as the upward step, you can't control it anymore as soon as you go with your x above your largest observed value x max. So you can fail arbitrarily badly if you just use a standard L1 regression. And with a pre-additive noise model we use in regression, you can actually go beyond the boundary a bit. Of course, not forever, but it allows you to get a fit where you can show that your population optimizer is actually the true function outside of the support you've seen. And the reason it works is essentially that the noise you have in the pre-additive noise model allows you to explore the structure of G once you go with X a bit outside of the support of the data you've seen. And it has an interesting effect that actually the amount you can go beyond the support you've seen is larger the more noise you had in the data. So noise in this case helps you so that your fit doesn't immediately break down at the boundary of the support. This is a simple example. It's a air quality data example. You might have seen it before. So it's just total nitrogen oxides on the y-axis against some non-methane hydrocarbons. Is a classic example. And here we split it into training and test in the way that the gray dots are the training data and the orange are the unobserved test data. And then you can look at what happens if you fit different methods. And the top left is just a linear prediction, right? You fit a linear model to the gray points, and then of course you just get the linear fit beyond that as well. On the top right is the fit you get from a tree or a tree ensemble as well, which would just be constant once you go outside of the support. Then the bottom left are the predictions you get from a neural network with different number of layers, so from 3, 5, 7 to 9 layers, and different random initializations. And there you see that the fit is pretty wiggly on the training data. And then what happens if you go to the test data, then it becomes pretty arbitrary. So you can get really wild kind of behavior as soon as it accesses outside of this support. And on the bottom right, you have the aggression fit. So the aggression really gives you the full distributional fit. Here, it's just shown what is the expected value of that. And it's using this exact same architecture as the neural network on the left. So it's using also 3, 5, 7, 9 layers with exactly the same number of hidden dimensions. And so what you see is that the fit behaves much more graciously, kind of if you go into the regime of the unseen test data. It doesn't behave as erratic as a standard kind of neural network fit, even though the architecture is really the same kind of. The difference is that we use a distributional approach, kind of, which stabilizes the fit. Okay. Questions so far? I'm not sure I can see it actually. If someone is raising their hand, I'll just assume there are none. And so here for the six models, the question is, does that actually work? So if we use aggression kind of for these different kind of building blocks, what happens if we try to go to this question mark in the square? So if we try to look at what happens to a model where, in this case, we've just used historical data, and now we look at the behavior if we use a forcing induced shift, which is way outside of that. So it's outside of the support. And again, there are two ways this can work. One way is that there's actually no interaction left, and that once you get the model induced shift and the forcing induced shift, which we can estimate really well, then there's not much of an interaction effect left. And this is broadly the case here. So there's not much kind of interaction left, but there is a small amount left, which we still fit kind of with this generative approach. And these are time series you see for the global mean for all the 10 variables I showed you in the beginning. And the blue is the unseen Yuki ESM data, and orange is the stochastic kind of model output. So it's like one time series kind of realization of the global mean, and ideally they should come from the same distribution. And so you see it works pretty well. Maybe the largest difference is for pressure, which is kind of a funny one if you look at the global mean anyway, because the total air mass should be conserved. And this is the same if you don't look at global mean, but you can look, for example, at global 80% quantiles. And so you see, you also get a pretty good match between the stochastic model output and the unseen data here. So it just saying that empirically, it seems like this approach mostly gets it right. And of course, the hope is that the same is going to be true if we go to error 5 data. So if we do this kind of bias correction, but of course for the error 5, since it's observational data, we don't have any kind of future outcome yet on which we could validate. So that was the first part about bias correction, which, as I said, is not strictly kind of necessary, but it's something nice kind of we can do on top. And now I want to talk a bit about the challenges, both statistically and computationally, for building a model like that. Right. So the problem is, in the sense, you have about 10 million kind of variables. So it's straightforward generative approach where you just build, you have your kind of 12 inputs, and then you have 10 million kind of outputs, and you use aggression loss is not going to work, because it's computationally quite hard, and also statistically the energy score doesn't have the power in this very high dimensional space to get a good power between any mismatch in your high dimensional generated samples. And so we want to use this reverse Markov learning, which is like an extension of aggression in a sense. And here's a simple example. What happens in 2 dimensions if the true data come from a Gaussian kind of mixture with 3 mixture components and you fit an aggression model, then it gets it mostly right. But you have some annoying dots on the lines which connect these 3 cluster components. And the reverse Markov learning approach is on the right. So it's like a multi-step approach of aggression. In a sense, you build several kind of aggression models in a row, and I'm trying to explain in a second how this works kind of broadly. So the underlying idea is the same as in diffusion models or in flow matching. Kind of you have a stochastic process which takes your data which you have and is trying to match it to a known distribution, like a standard kind of normal distribution. So what you have just discrete time slices here. So the idea is that y capital of T is really the distribution that you have, and y0 is like the endpoint of that forward stochastic process, and it's the distribution that no, sorry, y0 is the unknown kind of target, and y capital T is the known kind of distribution, like a standard Gaussian kind of distribution in high dimensions. And the most famous example are diffusion processes where you just go from step to step and you add a small amount of noise. And so you make, for example, an image, you make it noisier and noisier. And then the idea is that in the end, you try to revert that process if you want to generate a new image, for example. There's a linear interpolation where you say, okay, I have one sample from the distribution that I want to fit. There's another sample from, say, a standard Gaussian, and just connect them with a straight kind of linear path. And then you get something which is pretty much used like that in a technique called flow matching, because you can then also try to revert that process. What we try is something closer to this example 3, where the key difference is that for these 2 first examples, the forward path always stays in the same kind of dimension. So if you start in dimension 10 million, your forward path is also always going to stay in a 10 million kind of dimensional space. And this makes it really computationally hard for these kind of high dimensions. But here you can also use a different kind of approach. You can say, as I go on this path, I'm actually going to reduce the dimensionality. So for example, I can use a spatial pooling. And so I bring down the dimension of my xt at every time I use this kind of spatial pooling. So I want to show you a picture of how this kind of happens. So this is the original high resolution quarter degree grid data for temperature. And the dimension of this is close to 1 million, right? And then you say, okay, now apply the spatial pooling kind of operator. So I reduce each dimension by a factor of 2. So I get a reduction in P of a factor 4. And then I end up with an image with 200,000 kind of dimensions about. And so you don't see much of a difference here on the slides because the resolution is not good enough to show you kind of the effects of the higher grid time before. But if you do it again, you get like about 50,000 points, and you see it starts to become a bit blurry. And you can do it again, and then you have 12,000 about 3,768. 192, 48, and in the end, kind of if you do it again, you have only 12 global kind of grid points. And what we use here is the heel pegs grid. So you have each grid corresponds approximately to an equal area on the sphere. So it's a well-established kind of coordinate grid. This is like the forward path. So it's a simple kind of spatial pooling, and one advantage is really computational. So the last part is in a 12-dimensional space, which is really easy kind of to handle. There's also a statistical part to it, and one related to how these models really change. And the statistical part is that if you want to understand how does the distribution actually change in this 12-dimensional space, given my different forcings, then this is a much easier challenge than to think about it in a million or 10 million kind of dimensional space. So you can really make sure you get this 12-dimensional part right, which is a fairly low dimensional kind of problem. And then from there, you go back. And so in this lower dimensional part, you can really control the typical making. So, for example, you can make sure also that the global change of temperature, precipitation, and so on, that you get that exactly right, which is much harder if you have a diffusion process which stays in this high dimensional space. Okay, so this is kind of the forward path. And the idea is now to you say, okay, the observation is on the left, and now I build a simple regression model to generate, for example, two samples from this 12-dimensional distribution, or I have 10 variables, so it might be 120-dimensional kind of distribution. I get two samples. I have two samples. I have my kind of regression loss. I can optimize that, and so I can try to get a generative model in this fairly low dimensional space. And on the right, you see two samples kind of from that model. And now you go back on this path. So you would say, okay, I fix the samples I've seen at dimension 12, and now I go back to the next dimension, which is 48. And again, observation is on the left, and then you have these two generated samples with dimension 48 now. And the way you do it is, here is to say, if I want to go from the grid on the left, which is the low resolution one, to the higher resolution one, suppose I'm at the blue point on the right, then the way the current model works is to say I take a neighborhood of points in the low dimensional grid, which might be 16 neighbors of the blue point in the low dimensional grid. I have at each point I have the 10 observed kind of variables. I can add additional independent noise, and I can also add an embedding for what model I have, kind of what season I'm in, and the forcing. And then I have a location-specific sparse linear layer, which is transforming all these variables into a latent space. And after that, I use the same MLP across all kind of locations. So the MLP part is really shared, but each location gets its own sparse kind of linear layer. And the advantage is that, as opposed to standard convolutional approaches, that for these data, each location has a very specific meaning. So there's no sense of translation kind of invariance, which you would assume generally for convolutional models. And it really does matter if you pick a point which is, for example, Mount Everest, or if you pick a point which sits in the middle of the Pacific. The dynamics are going to be different. The way we take account here is just to fit the sparse linear layer. So it doesn't contain too many parameters, but it can adapt to each location. And if you take another point here, in New Zealand, then your neighborhood is going to be those red points here, which are kind of the closest 16 neighbors for New Zealand on that grid. And so you go back to a high dimension grid, and then you repeat this game. So you go from 198, 92 dimensions, you go to 768, 3000, and you continue this game. And of course, if you come to the higher kind of resolutions, computationally, it becomes a bit harder because you just have bigger models. The good thing is that the most complicated part from a statistical point of view, like all the induced distributional changes and so time dependence as well, happens mostly at the lower kind of resolution. So the statistical part is really hard to get right for the low kind of resolutions, but then for the higher ones, it's essentially only a computational game. Up to this 1 million kind of dimensional space you go back. Yeah, and the advantage is really that you get a pretty lightweight kind of model, and in terms of runtime, I mean, I said already, the original physics-based model for 100 years would take a few weeks kind of to run on a supercomputer. If you were to run a diffusion-based model for the same kind of data, I don't even know if you could actually fit it. Maybe if you're NVIDIA, you could do that with a large kind of cluster. But even if you had the model to produce 100 years of samples, would take approximately kind of 8 hours on an L4, so mid-range GPU, and currently this approach takes only kind of 20 seconds because we make use of that. The majority of the path is really in this much lower dimensional space. Okay, and the same, for example, for presentations. So here would be an observation, and the forward path is taking us down to a coarser and coarser kind of representation. And then you build a model in this low dimensional space, and then you go back to a high dimensional one. So this would be, again, kind of the observation on the left and 2 samples on the right using exactly kind of the same approach. And actually it's done simultaneously for all 10 variables. So you try to take account of so correlations between kind of these variables as well. Then the question is, how do you evaluate it? And there are a range of metrics we're using. For example, kind of bias maps. Here's how much bias you get if you use that approach for example, wind speed. There are things like you can look at, okay, I mean, the model didn't know anything about El Nino, but you can say, okay, if I simulate data from that, how does the implied El Nino frequency curve or the power spectrum kind of looks like? And I apologize for the name here. This was not my kind of invention. It was my brother kind of named it like that. So you have the blue one is the true El Nino, and then the orange curve is the time series you get from the model if you really generate the time series in this full dimensional space. And from that, you say, what is actually the El Nino indicator for that kind of model? And you plot the time series kind of over the years. And you see that you get a match in the frequency spectrum kind of broadly. I mean, it's definitely not perfect, but it broadly kind of matches it. So you get a peak at about a 4-year kind of rhythm. Then physicists like to look at what they call teleconnections. So teleconnections is nothing else than saying, okay, you have this El Nino going on. How do other variables respond to that? So this is essentially just saying I regress at each location. I regress the variable onto that kind of El Nino index. And here is it done for precipitation. So you see green would be where it rains more if you have a high kind of El Nino index, and orange is if it rains less. And on the left, you have the true data in a sense, and then on the right, you have an image where what you get from the model. And so you see you get broadly a good match kind of between these two. And here it's the regression is also done kind of independently by location. And so you see you broadly get a good match, even though you didn't put that into kind of the model fit in the first place. And you can do then certain things with it. You can do kind of event attribution, which is like a counterfactual question. Like if you have an extreme event, you can ask how different would it have been if the forcing would have been kind of different, which is often used in the legal context, for example. You can do things like model uncertainty, quantification, intervention experiment, and seasonal predictions. So for example, here's a plot like what is the wind speed change on average across all these CMIP6 models, and then on the right you see how much do these models actually differ per location. So you see the areas of red are regions where the models have not a high degree of giving the same kind of answer, and the blue regions are regions where the models tend to agree on the average wind speed change you're going to get. So it allows some sense of to get a sense of where do these different kind of physical models actually agree and where do they not agree for new scenarios. You can do the same for something like maximal wind speed change over all models. Or here's an intervention experiment where you can say, well, what would happen for the current climate if I remove all kind of aerosols from the atmosphere, which is of course good from a health point of view, but what has happened, for example, to the DTR, which is the diurnal temperature range, which is the average difference between maximal and minimal temperature you get per day. So how large is the range you're going to get in temperatures per day? And you see the effect of aerosols is mostly blue, and blue means it's kind of squashing this DTR, so it's making the extremes less pronounced because you have clear skies during the day, and so you get higher temperature, so peaks, and you also get kind of colder nights. And the effect is especially pronounced in China. It's the darkest blue, I guess, just because it had kind of the highest aerosol concentrations, and you see it's reversed over India, which seems to make sense from what I learned, because their aerosol is mostly due to black carbon from burning a lot of wood and so on, and this has different cloud forming effects. So it kind of makes sense that the effect is different for India because of that black carbon kind of concentration. And finally, you can do things like seasonal predictions. So you can plug in kind of the current state, and you can try to forecast. You can try to forecast what is going to be the temperature in 1 month, 2, 3, and so on up till 12 months. And so here you see the correlation with the actual kind of outcome at these different lead times. So 1 is top left, then 2 is top kind of middle, and so you see you have a better predictive accuracy, obviously, for shorter kind of lead times. And then at 12 months, you don't have so much kind of left, but it's broadly in line with what seasonal prediction can do at the moment if you have kind of standalone models. And it's also observable that you can do better for the tropics than for some kind of other regions, which also makes physical sense. Okay, so this is the summary. Summary is that if you use regression and reverse, so Markov Learning, you can build these emulation of these GCMs, and it's not. I mean, it's really easy to fit in a sense. You don't need a GPU cluster for that. In fact, it's fitted on 2 kind of or 4 of these rather mid-range GPUs. It's not a particularly good one. It allows some sort of bias correction between kind of models and observational data. And once you have it, you can do all these different things like event attribution to model uncertainty, intervention experiments, and seasonal prediction. And I'm right on time, so thank you for listening. And I'm happy if you have any questions.
Thank you very much, Nicolai. If there are questions, I think that you should feel free to unmute yourself. Or if you prefer, you can also write your question in the chat.
Oh, can I see the chat?
Elizabeth, you have a question.
Yes, I do have a question. Thank you. Very interesting talk. You mentioned when you were talking about the reverse Markov learning, this successive coarser grid kind of then work backwards, actually working back across finer grids. You mentioned that you do this for the multivariate data to take advantage of the dependence. And I'm curious, are you also doing it with respect to time? So do you also have the grid in time? Yeah.
Yes. So the time dependence is built at different kind of resolutions. I didn't go into that so too much, but the idea is also that it helps you on that kind of level as well, because the strongest time dependence happens actually for the courses grid. So there is a time dependence model, which is essentially an AR model, which goes back kind of 3 years, and it's built at the courses level. And once you have these predictions, there's another one at the next higher kind of resolution, and so on. So there's a hierarchy of these time dependence kind of models. But at some point, like if you get to dimension above 3000 and so on, there's actually not much time dependence left at the scale. It's all happening at the lower kind of resolutions, which is another reason it actually makes sense to have this kind of dimensionality reduction, because it's much easier to get the time dependence right in the low dimensional space than in the high dimensional space.
I see. And so is that time dependence also part of the locality estimation you mentioned, where you have this neighborhood
Yes.
structure? Yeah.
Yes. So it adapts to that kind of locality as well. Yeah.
Exactly. All right. Thank you very much.
Thank you.
Any other questions?
Can I ask one question?
Of course.
Thanks for the excellent talk. So how can you comment a bit on how the forward process would affect the result, like how easy it is to learn the backward process? For example, I was thinking currently you're doing average pooling, but have you thought about max pooling or like some?
Yeah, I tried that actually. I tried a combination of mean pooling and max pooling. But it actually got harder kind of to learn for some reason I didn't fully understand, I think. But somehow if you're then on the reverse path and you've conditioned on the mean and the max, you need to get the conditional distribution right. With the high resolution one, conditional on knowing the mean and the max. And that seems to be a harder problem than just conditioning on the mean. So in the end, it turned out that just using the mean was actually the simplest and also gave the best result.
How much do you think actually those domain knowledge, like the physics knowledge, would benefit the design of the forward process? Because
I think in this case it just helps a lot, because the physicists like to look at these low dimensional things, like, for example, what is the global mean, or what happens to Western kind of Europe. These are intuitively, these are the things kind of that want to look at first and try to get them right. And so if something goes wrong in the generative kind of process, and it happens already at this early kind of resolution stage, you can really identify it quite clearly and easily, and people know if it makes sense or not. Whereas if you start with a really high dimensional space, and suppose your global temperature comes out wrong, you don't really know how the problem happened. And so I think in that sense it's more interpretable for the physicists, and it's easier to communicate kind of with them as well on it.
have you tried learning the forward process instead of having the just average pooling?
I have not. This would be something interesting to try.
Okay, thanks.
Thanks.
Yanqi.
Hi. Oh, yes, it's great talk. So I'm wondering, when you are learning the backward process, are you using the same? So it's going from the lower resolution to the higher resolution, right? So are you using the same prediction model across every regions, or you are more using like a tailored to every layer? Because I could imagine if you doing too finer model, it's probably going to become very computationally expensive.
So there is one part which is location specific, and then there's one part which is set. So the location specific part is really just this very sparse kind of linear layer where I showed the plot where each point is just looking at a neighborhood and is summarizing all the information in this neighborhood with a sparse kind of linear layer. So it's not too many parameters you have to fit there. And after that, everything is shared across all kind of locations.
So also
So
for
it
the
has
resolution, yep. Go ahead.
so for the resolutions, no, I mean each resolution kind of works on its own. So you kind of fit a separate model for each of these resolution steps. So they are kind of independent. In fact, you can train them kind of independently of each other, and you just plug it kind of together in the end.
I see. Okay, thank you.
And can I just like comment a bit on that? Because the thing is, in diffusion model, you always operate on the same dimension, so you could share the score function for each time step, and you just have a time index, time embedding in your model, so you could share that. And for our method, if we also define the forward process in a similar way, like always in the same dimension, we could also do that. So we could also just put a time embedding in the model. But the thing is, we are reducing the dimension each time, so it's kind of we kind of have to use separate models. Although maybe we could also be creative and thinking of some like masking ideas here to just still share some part of the parameters. That would be cool. Yeah.